The dawn of the final phase of the Battle of the Atlantic witnessed a dramatic technological shift that promised to redefine the parameters of naval warfare. For 5 years, the Kriegsmarine had waged an exhausting war of attrition using the Type 7 and Type 9 submarines, vessels that were not true submarines but rather submersible torpedo boats. These older craft spent more than 90% of their operational lives on the surface, utilizing their diesel engines for propulsion and only submerging to conduct stealth attacks or evade Allied escorts. Once submerged, their speed plummeted to a crawl of barely 7 knots, and their lead-acid battery capacity was so restricted that they were forced to resurface within 24 hours to recharge, exposing themselves to the increasingly lethal radar and aerial patrols of the Allies. In response to this crushing tactical bottleneck, German naval designers sought a revolutionary leap in underwater capabilities, initially pinning their hopes on the Walter hydrogen peroxide gas turbine. The Walter turbine promised exceptional underwater speeds, but it was plagued by severe fuel safety hazards and severe production bottlenecks of high-test hydrogen peroxide, forcing the Kriegsmarine to pivot toward a more conventional yet highly expanded solution. This technical pivot gave birth to the Type XXI Elektroboot, a vessel designed from its keel up to operate entirely submerged and independently of the surface. Rather than relying on the unproven and volatile Walter turbine, engineers under the direction of Helmuth Walter and the German Naval Construction Office expanded the conventional battery capacity to an unprecedented degree. By replacing the traditional keel structure with a deep, figure-8 cross-section pressure hull, designers created a massive, 3-deck lower battery compartment that housed 3 times the electrical storage capacity of previous designs. This massive energy reservoir powered 2 high-performance electric motors, supplemented by 2 silent running creep motors that could drive the submarine through the water with almost zero acoustic signature. The exterior hull was stripped of all traditional deck guns, deck railings, and external storage lockers, creating a perfectly streamlined hydrodynamic teardrop profile that offered minimal water resistance. The conning tower was transformed into an enclosed, organic sail that housed the retractable snorkel masts, radar detectors, and periscopes, all coated with rubberized anti-radar materials to defeat Allied sensing arrays. The performance specifications of the Type XXI were staggering on paper, representing an exponential leap over any submarine then in existence. While a Type 7 struggled to reach 7 knots submerged for brief periods, the Type XXI could sustain an underwater speed of 15 knots for several hours and sprint at an astonishing 17.9 knots to outrun Allied escort vessels. Its passive sonar array, known as the Bohrkonjurat, was housed in a bulbous dome at the bottom of the bow, allowing the crew to detect, track, and target multiple convoy vessels simultaneously without ever raising a periscope or exposing their position. Combined with a revolutionary hydraulic semi-automatic torpedo loading system that could reload all 6 bow tubes in under 20 minutes, the Elektroboot was theoretically capable of decimating an entire convoy single-handedly from the safety of the deep. This was the submerged revolution that Albert Speer and the High Command believed would turn the tide of the war, yet this physical marvel would soon collide with the harsh limits of the rise-collapsing industrial base. By the summer of 1943, the relentless Allied bombing of German coastal cities had severely damaged the traditional shipyards of Hamburg, Bremen, and Danzig, threatening to halt submarine construction entirely. Recognizing that traditional slipway assembly was no longer viable under the weight of Allied air superiority, the newly appointed Minister of Armaments, Albert Speer, initiated a radical industrial reorganization of the entire German shipbuilding program. Speer recognized that building a submarine on a single coastal slipway from the keel up was too slow, too vulnerable, and too dependent on localized marine labor. He proposed a massive, decentralized modular manufacturing scheme that would apply the principles of Henry Ford's automotive assembly lines to the production of major naval combatants. Under this new plan, the complex pressure hull of the Type XXI Elektroboot was mathematically dissected and divided into 8 distinct, standardized sections, designated Section and I through 8, starting from the stern and moving toward the bow. The core of Speer's prefabricated fantasy lay in utilizing the vast, undertapped industrial capacity of the German interior, far away from the coastal regions that were within easy reach of Royal Air Force bomber wings. Speer established a specialized main committee for shipbuilding, led by civilian industrialist Carl Otto Sohr, which bypassed the traditional naval construction corps and handed the manufacturing of individual hull sections to inland structural steel firms, boiler makers, and bridge building companies. These inland firms, situated in the Ruhr Valley, Silesia, and central Germany, were tasked with fabricating the steel plates, welding the internal structural frames, and pre-installing all the internal machinery, piping, electrical wiring, and auxiliary equipment within their assigned hull section. Once finished, these massive modular sections, weighing up to several dozen tons, were to be loaded onto inland canal barges or specialized heavy rail flatcars and transported across hundreds of miles to the coastal assembly yards. At the final coastal assembly shipyards, such as Blohm and Voss in Hamburg, Deskimag in Bremen, and F. Shisho in Danzig, the slipways were to be transformed into simple assembly lines where workers would merely align the 8 prefabricated sections and weld them together into a complete hull in a matter of days. This modular assembly scheme was projected to slash the construction time of a fleet submarine from nearly 9 months down to a mere 6 to 8 weeks, allowing the Kriegsmarine to flood the Atlantic with hundreds of Type XXI boats by late 1944. The German propaganda machine hailed this program as a masterstroke of National Socialist industrial genius that would bypass the physical constraints of geography and bombing. However, the planners in Berlin had failed to account for a fundamental physical law of naval engineering, which dictates that the margin of error for a structural steel bridge on land is vastly different from the margin of error for a vessel designed to withstand the crushing hydrostatic pressures of the deep ocean. The fundamental flaw of Albert Speer's modular manufacturing program lay in a profound culture clash between the tolerances of civilian structural engineering and the unforgiving precision of naval architecture. Inland steel firms, boiler makers, and bridge builders were accustomed to manufacturing large-scale civil infrastructure where a dimensional deviation of several centimeters was easily corrected on-site with sledgehammers, heating torches, or additional shim plates. For a bridge crossing a river, a slight variance in a structural beam had no impact on its overall integrity, but for a submarine pressure hull, which must distribute thousands of tons of hydrostatic pressure evenly across its circular cross-section, even a minor deviation of a few millimeters is catastrophic. When the modular sections of the Type XXI began to arrive at the coastal shipyards via canals and rail, the final assembly teams were horrified to discover that the individual sections were fundamentally incompatible with one another. The circular flanges, bulkheads, and mating rings of adjacent sections were warped, out of round, and off-center by several inches. The structural frames inside the sections, which were supposed to line up perfectly to provide continuous rigidity throughout the length of the pressure hull, were misaligned and buckled. Because the inland firms had welded the internal machinery, heavy piping, and electrical conduits into the sections before shipping, the structural distortions had also twisted the delicate interior fittings, making it impossible to connect the fuel lines, hydraulic systems, and steering linkages between sections without severe force. The coastal shipyards, which were supposed to act as rapid assembly centers, were instantly transformed into massive, chaotic repair shops where the speed advantages of modular prefabrication were entirely wiped out. Instead of rapidly welding the modules together in a few days, shipyard workers at Blohm and Voss and Deskimag had to spend thousands of agonizing man-hours correcting the errors of the inland manufacturers. Workers had to use heavy carbon arc gouging equipment to cut away misaligned structural frames, apply massive hydraulic jacks and propane heating rings to force the warped pressure hull sections back into a true circular shape, and hand grind the mating flanges for weeks just to achieve a seal. This agonizing rework had to be conducted under the constant threat of Allied air raids, which frequently severed power lines, destroyed shipyard cranes, and shattered the delicate alignments of the hulls on the slipways. The millimeter bottleneck proved that the industrial fantasy of mass-producing precision naval craft using non-marine labor was an expensive delusion, as the shipyard labor hours required to assemble a single Type XXI skyrocketed far beyond the hours needed to build a traditional Type 7 from scratch. The structural and mechanical legacy of the Rush Type XXI program was defined by a series of critical engineering defects that made the submarine as dangerous to its own crews as it was to the enemy convoy escorts. Because the vessel had been pushed from the drawing board directly into mass production without a proper prototype phase or extensive trial periods, basic mechanical systems were riddled with fatal flaws. The most notorious of these lay in the complex, high-pressure hydraulic system designed to operate the massive dive planes, the heavy rudder, and the semi-automatic torpedo loading gear. The designers had selected standard industrial-grade hydraulic fluid, which performed adequately during warm weather testing in the Baltic Sea but proved utterly useless in the freezing, sub-zero depths of the North Atlantic. In the cold ocean currents, the hydraulic oil became thick and sluggish, resembling a dense sludge that clogged the hydraulic valves and caused the steering linkages to lock up, frequently trapping the submarine in uncontrollable dives or leaving it helpless on the surface. Equally catastrophic was the structural weakness of the pressure hull itself, which was a direct consequence of poor welding standards and low-quality steel plates supplied by the inland manufacturers. The internal framing ribs, designed to prevent the double hull from collapsing under hydrostatic pressure, were poorly welded to the outer plating, with many joints containing large air pockets and slag inclusions that compromised their strength. During deep dive trials, the structural ribs began to warp and buckle at depths far shallower than the design limit of 280 meters, forcing the Kriegsmarine Command to restrict the safe operational diving depth of the entire Type XXI fleet to just 150 meters. This restriction stripped the Elektroboot of its primary defensive weapon, which was its ability to dive deep beneath the thermal layers of the ocean to escape the sonar and depth charges of Allied destroyer groups. The internal environment of the Type XXI was also a toxic trap, especially within the massive, triple-deck battery compartment that formed the heart of the boat's propulsion system. Because the rushing of the assembly lines had prevented the installation of proper ventilation systems and acid-resistant liners, the massive array of lead-acid batteries was prone to overheating and leaking corrosive battery acid directly onto the steel frames of the lower hull, initiating rapid structural corrosion. Furthermore, during high-speed underwater runs or rapid recharging cycles via the snorkel, the batteries vented massive volumes of highly explosive hydrogen gas that accumulated in the unventilated corners of the lower decks, creating a constant hazard of internal explosions. The structural and mechanical reality of the Type XXI was a far cry from the sleek wonderweapon of propaganda, as the crews found themselves confined inside a complex, fragile, and structurally compromised vessel that was plagued by sluggish oils and flawed steel. The mobilization of Germany's industrial resources to construct the Type XXI fleet represents one of the most short-sighted economic decisions of the late war period, demonstrating the immense opportunity costs that accelerated the physical collapse of the Reich. By late 1943, the German war economy was facing acute shortages of raw materials, particularly high-grade structural steel, copper, and electrical components, which were vital for maintaining the nation's crumbling infrastructure. Despite these severe shortages, Albert Speer and the Naval Command committed thousands of tons of high-grade steel and immense quantities of copper to the Type XXI program, prioritizing the mass production of a weapon system that had yet to prove its operational viability in combat. This massive extraction of resources directly starved the German national railway, the Deutsche Reichsbahn, which was the literal lifeblood of the domestic economy and the military supply lines. The Reichsbahn was responsible for transporting millions of tons of coal, steel, munitions, and agricultural goods across the country, but by 1944, its locomotive fleet and rail network were disintegrating due to a complete lack of maintenance and replacement materials. The high-grade steel that was desperately needed to manufacture new steam locomotives and repair shattered rail junctions was instead being diverted to the inland fabrication yards to build the pressure hulls of the Type XXI. The massive copper allocations required to wind the complex electric motors of the Elektroboot directly stripped the electrical grid and the locomotive repair shops of the wiring needed to keep the transport network running. As a direct consequence of this starvation, the Reichsbahn's capacity to move raw materials collapsed, leaving coal sitting at the pit heads in the Ruhr while steel mills in Silesia shut down due to a lack of fuel. The systemic economic feedback loop was devastating, as the collapse of the railway transport network prevented the delivery of the prefabricated Type XXI sections themselves to the coastal shipyards. Massive hull modules lay stranded on canal barges that could not move because the canal locks had been destroyed by Allied bombers, or sat on rail flatcars in remote sidings because there were no functioning locomotives to haul them to the coast. By prioritizing the high-technology fantasy of the Type XXI over the unglamorous necessity of rail maintenance, the German leadership guaranteed the paralysis of their own industrial base. The opportunity cost of the Elektroboot was not merely measured in failed submarines, but in the systemic starvation of the transport network that made the continued production of all armaments physically impossible. The final historical audit of the Type XXI Elektroboot program is a sobering testament to the futility of introducing advanced technology without the industrial precision and economic stability required to support it. By the time of the German surrender in May 1945, the coastal shipyards had managed to commission 118 Type XXI submarines into the Kriegsmarine, a number that appeared impressive on paper but hid a devastating operational reality. Out of this vast fleet of commissioned vessels, only 4 were ever certified as fully combat-ready by the Naval Testing Command, and only one single submarine, U-2511, commanded by the experienced veteran Albert Speer, ever managed to conduct an active patrol before the war ended. The remaining 114 submarines sat idle in the harbors of Norway and the Baltic, plagued by structural defects, incomplete wiring, and a total lack of trained crews, diesel fuel, and battery replacements. U-2511's brief patrol in May 1945 demonstrated both the potential of the design and the ultimate irrelevance of its technical achievements in the face of total strategic collapse. While Speer successfully utilized the boat's silent creep motors and passive sonar to slip undetected beneath an Allied destroyer screen, the patrol was cut short by the German surrender order, and the submarine returned to port without firing a single torpedo. The grand modular dream of Albert Speer had yielded nothing but a series of expensive, non-operational steel tombs that were scuttled by their own crews or captured by the Allies to be analyzed as technological curiosities. The design of the Type XXI would heavily influence post-war Soviet, American, and British submarine development, particularly in the creation of the Soviet Zulu and Whiskey classes and the American Greater Underwater Propulsive Power Program, but for the nation that conceived it, the boat was a total industrial failure. The legacy of the Type XXI is not one of military triumph, but of a desperate, resource-intensive failure that proved a weapon system is only as viable as the domestic economy and industrial quality control that underpins its construction. The attempt to bypass the physical realities of marine manufacturing through decentralized prefabrication ultimately accelerated the defeat of the German war machine, demonstrating that complex engineering cannot be rushed or faked on a collapsing assembly line. The prefabricated trap of the Elektroboot serves as an enduring historical lesson on the dangers of the wonder weapon myth, illustrating how a nation can exhaust its final industrial reserves chasing a high-technology fantasy while its vital infrastructure crumbles into ruin.